Welcome to the presentation of our paper, Differentiable Dynamics for Articulated 3D Human Motion Reconstruction. My name is Erik Gartner, and this is joint work together with Mihailo Andriuka, Erwin Kumas, and Christian Smikoszewski. In this work, we present our method for physics-based human pose estimation through the inclusion of a differentiable physics simulator. Prior work in human pose estimation commonly attempt to solve the ill-pose problem of estimating 3D poses from binocular video using deep neural networks that predict 3D poses either directly or by first detecting 2D poses and then lifting them to 3D during a second step. These kinematic-based methods have been trained to solve this underdetermined problem by learning from large human motion datasets. While this may work for common poses, it often leads to non-physical artifacts, as these methods are purely statistical and do not consider any physical constraints such as gravity, collision, ground plane location, or friction. In the example below, our semantic predictor accurately detects the person and produces 3D poses that align well with the image. However, when viewed from another camera angle, we see that the predictions do not walk but rather float forward above the ground. We hope to address these types of artifacts by making physics a first-class citizen in the reconstruction process. Compared to recent physics-based methods, our method is the first differentiable approach which features full body contacts without limiting to foot-ground contacts, and while also demonstrating results on real-world video captured outside of laboratory conditions. Our method, Diffie, approaches the task in 3 steps. In the first step, we extract visual evidence in the form of 2D body key points, 3D poses, semantic body segmentation, and body shape estimates using the Hund neural network predictor. We then estimate the ground plane location and the world-to-camera transform. In the second step, we construct a physical body model to represent the observed subject in the physical simulation. In the third step, we optimize a reconstruction loss between the motion inside a differentiable physics simulator and the observed visual evidence. This results in a reconstructed motion that is as close as possible to the observed motion while still respecting the constraints of physical simulation such as contacts and gravity. We use a physical body model based off and sharing the same kinematic structure as the statistical model GUM. This allows us to seamlessly go between the GUM pose representation and the physical model for a subset of 16 body joints. Given a body shape expressed in the GUM latent shape space, we adapt the shape, mass, and inertias of the physical model. We first predict the mass of the physical model from the volume of the GUM mesh using a regressor trained on the Caesar dataset, and then distribute the body weight according to medical models of body mass distribution. Shown here is an overview of our differentiable physics loss. Given time-varying joint control targets Q hat, the initial state of the simulation S0, and the physical body beta, we unroll the simulation for capital T time steps. The physics loss is the sum of the reconstruction losses between this visual evidence and the motion performed in physical simulation at each time step. In cases where the initial frame is either occluded or simply poorly estimated, we include the initial state of the simulation as a variable to optimize, thus allowing us to recover from poor initial states. Similar to prior work, we infer the torques in the body using PD control, where the torque is proportional to the error between the joint targets Q hat and the actual joint angles Q. We optimize our loss using the global optimization method Bayesian together with the gradient-based BFGS optimizer. Our reconstruction loss is a weighted combination of 4 terms. Firstly, a 3D center of mass loss that tracks the character's global translation, a 2D reprojection loss to align with the image, a joint angle loss, and a joint limit regularizer based off the GUM model's anatomical limits. We evaluate our method on the standard pose dataset Human 3.6M, the AIST dance dataset, and in the wild internet videos. And we observe that our method reduces joint error as well as jitter and foot skating in the motion. We also note that our combination of global optimization using Bayesian together with BFGS gives better results than using only BFGS while requiring a fraction of the compute compared to a gradient-free approach. We now return to the floating example from the beginning and note how Diffie recovers plausible leg motion. Unlike prior work, Diffie supports the combination of full body contacts and unknown ground plane as shown in this qualitative example on an uncontrolled internet video. Thank you for listening, and please visit the link below for more information.